Back. I still have notes here for those who still do not have them. Okay, so last week we looked at events and probability. We actually finished the first subpart of the module, and we started looking at random variables, especially discrete random variables. So if you remember, we talked about random variable x as essentially function that goes from my sample space to real. And so I gave you, for instance, this example where we play dart, and actually any points here in this quarter would be a certain value 10, for instance, if actually your score is 10, right? So x here is a random variable that actually represents the score when you play dart, right? And so we discussed this last week. We said, well, we can have random variables that are discrete and continuous, right? And what we started looking at is the discrete case. And so here is an example where actually x, your score when you play dart, is an example of actually discrete random variable that can take values between 1 and 60. Right, so first thing actually we looked at is the notion of a probability mass function, or PMF, right? That says that if I have a certain random variable x, right, fx of x here represent the probability that x is equal to small x, right? And how do we represent this? We can have x can take, for instance, value x1, x2, x3, all the way to xn. And this probability mass function is every time evaluated at x1, x2, x3, all the way to xn. Right, so it's really a probability. It really gives you the probability that x is equal to that specific value, right? So there are two properties that we looked at. We first said that, well, f of x has to be larger or equal to 0. And the second one was that if you sum over all possible I, this probability mass function, you should get 1. Okay? Good, so that was the notion of probability mass function. We looked at the notion of CDF, or cumulative distribution function, which is essentially now the probability that x is smaller or equal to a certain value, x, right? And so here in this case, when you have discrete random variable, you have x1, x2, x3, and so on. Essentially, this CDF takes the shape of a kind of staircase like this, where you have an increase every time you reach one of those values within the range of the random variable. Then we looked at expectation of x, which is also called mu, right, or theoretical mean, right? And so what did we say there? This is a weighted sum. It's a weighted sum, so I sum over the range of this random variable over all value of x, and I weight by this probability mass function. Okay, so what does that measure? That measure where on average distribution is centered around, right? So for instance here, if I have a distribution that says I have 1, 2, 3, and 4, and I have something like this that have value of, I don't know, 0.2, and here I have value of 0.3, right? You see that actually this distribution is centered around 2.5. Okay, so what does that measure? You can find similar notions in other fields, if you look at mechanics, for instance, you can understand this expectation as a form of center of mass, right? So you can imagine this is a form of support here, right? And you put 4 weights, 4 different weights, different distances here with different weights, right? And you're looking at where actually this is centered so that this support remains completely balanced, right? So this is a little bit the idea of this average or expectation. Right, then we looked at notion of variance. Variance of x, called also sigma square. Oops. Right, so variance of x, and we say this is expectation of x minus mu square. So it's the expectation of the square of the deviation between x and its mean. So what this measure is actually the spread of the distribution, or the spread of this probability mass function around its mean, right? So you can have, for instance, a distribution like this, or you could have distributions where, for instance, you have still those 4 values, right? But they are uniformly distributed, right? So you have values here, here, and here, and here. So here what you notice between those two is that maybe they have the same mean, but they have a different spread around the mean. Okay, so the variance is a measure of this spread. The larger the variance, the larger the spread around the mean, right? The smaller the variance, the more the distribution is concentrated around the mean. Okay? Good. Then we looked at some properties, and I had some questions about this after the lecture. So we had this quantity, for instance, right? And we said, well, this is essentially sum over all x of x squared multiplied by the probability mass function. Why? Still, something has changed here. That should work, right? Right. So where does that come from? Well, imagine when I'm taking expectation of x squared, what am I doing? What is x squared? X squared is still a random variable. So I can still write, for instance, y. Y is x squared. So x goes from the sample space and gives you a real value, right? Y, which is x squared, still go from the sample space and give you a real value, right? So when x was equal to 10, for instance, in your score, now I take a y that is equal to 100, right? So I can say x can take value x1, x2, x3, all the way to xn. Fx of x would take value fx, x1, fx, x2, all the way to fx, xn, right? When I'm looking at expectation of y, I can say, well, this would be a sum over y of y multiplied by this, right? Is the definition of expectation. But now my y is equal to x squared, right? So this is equal to a sum over x over all y, but now I will replace this by x of all x squared, right? And now what is fy of y? Well, y will take the value x1, this is y1, right? y2 will take value x2 squared, y3 will take value x3 squared, and so on. What is the probability of y occurring? This is fy at y1. This is actually the same here as the probability of x1 occurring, right? Because there is a one-to-one relationship, right? So if x1 occurs, y1 will occur, right? So this is why you see here that this quantity here is sum over x of x squared multiplied by xi over all xi. So here over all I. Okay, so here if I'm writing with I have all I, and here this is now replaced by this. Okay, so this is something that you will see extensively right? When you take an expectation of x squared here, you're taking the, essentially, you do not need to compute a PDF of a new random variable. You can take the expectation of that quantity directly. And what is an expectation is a weighted sum. So you actually take still this quantity, you sum over all those possible quantities, but you weight by the probability mass function, right? And this is something we're going to see today, again, with continuous random variables. Okay, so where is this used? Well, this is used when we looked at the variance. This is expectation of x squared minus expectation of the square of x, minus the square of the expectation of x, and this is always positive. Okay, so this is something we did last week. Okay, good. So with this today, what we're going to do is essentially look at different distributions or different form of probability mass function. So still discrete random variable, and the first one we can look at is a uniform. So it's a discrete random variable, but actually is uniformly distributed. So this is the simplest one, and a clear example is when you throw a die. When you throw a die, you have 6 possible outcomes, right? And they're actually uniformly distributed. Each of them has a probability 1/6 to occur, right? So here, my random variable x will be uniformly distributed when I have a probability mass function that is given by 1/k, and when I have essentially that x can take k values from 1 to k. So essentially, when you throw a die, k is equal to 6, so you have a probability 1/6 of a certain value to occur. Okay, so pretty simple. What is the probability, the cumulative distribution function? So this is our probability mass function, right? This is our cumulative distribution function. Well, it's the sum of this, is the sum over all possible values that I have here. So I, from 1 all the way to the value x, of the probability mass function, which is 1/k. So this is x/k for x equal to 1 to all the way to k, right? So here, indeed, you get the staircase like this. We have 1, 2, 3, 4, and so on. You have 0 here. At 1, you pass at, it becomes 1/k, then becomes 2/k, and 3/k, and so on. Okay? That's the simplest case you have, essentially. If you draw this, you get value 1, 2, 3, 4, and so on. And essentially, all of them have the same probability mass function here, is 1/k. Right? So this is the shape of the CDF. This is the shape of the probability mass function. Right? That's the easiest one, not super interesting, but we start with this. Okay, so what is the expectation of this quantity? What is the expectation of x? Well, you know from the definition, you sum over all x within the range of this random variable. So what do we have here? All those x goes from 1 to k, so I take the sum from 1 to k of x multiplied by 1/k. And so you can bring this out. You have 1/k, and here you have between brackets a sum x equal to 1 to k of x. And this quantity is something you can calculate. You can calculate for any values of x, and you get essentially that is something like this. So what you get is k plus 1/2, and what this means is essentially the value that is here. So if you have k is equal to 4, for instance, right, what will be this mean is 5/2, you're going to lie here at 2.5. Right, so this is an example here where you see that actually the mean, the expectation, does not belong to the range of this random variable. The range is 1, 2, 3, 4, for instance, if k is equal to 4. The mean or the expectation of that random variable is 2.5, it doesn't belong to that range. But that's not an issue. Right, so you can do the same with the variance. You can compute the variance of this random variable, variance of x. And how can you do this? You can say this is expectation of x squared minus the square of the expectation. Right, so this quantity here we have computed already is k plus 1 over 2. And so what you can compute this quantity here, which will be a sum over x squared of 1 over k, and you sum for x going from 1 to k. Okay, so this is something that can be done as well. What you get is k squared minus 1 over 12. And so what it means is as k increases, essentially the variance of that random variable increases, right? And this is quite natural. As k increases here, right? If I take k equal to 2, for instance, I'm going to have my probability mass function will be at 1 and 2. I'm going to have here 1/2. If I take k is equal to 4, I have here 4 values, right? And each of those probability mass function here is equal to 1 over 4. So what you see is that as you increase k, essentially that distribution becomes flatter, right? And more spread around its mean. Okay? So again, the mean is essentially you're looking at where the distribution is centered. The variance, you look at the spread of the distribution around its mean. Good. So this is probably the simplest one, right? The simplest probability mass function we can look at. A more interesting one is called binomial. Right, so I have a random variable, x, and I'm saying it has a distribution that is binomial distributed, and I denote it like this, bin np, with 2 parameters n and p. So when does that happen? What kind of scenario are we looking at? We're looking at an experiment where I have trials. I have a certain number of trials that is given by n. So I have an experiment here where I have n trials, but they're specific. N independent trials and identical. Right? So for instance, I toss a coin, and I do this n times. Every time each trial is independent, and it's identical. I don't change the coins. I don't change the probability of having a head, for instance. Right? So they're still identical. That's the first characteristic of a binomial. The second one is actually the outcome has to have binary. So you need to have binary outcomes. So that means that, and what we call it, is usually success or failure. Right? For instance, you toss a coin, you're looking at the head, right? Head is your success. And you can have n trial, 6 trial, where you toss a coin. And if you have multiple heads, this is what you call success. And the probability of success is called P. It's called P. So what does X look at? X is the number of success in n trials. Right? This is what we're looking at. So where can this be used? Well, if you have a communication system, and what you do is that you transmit here, you have a transmitter, you have a receiver, you transmit something, and you transmit bits of information here, for instance, right? So you can actually, to some extent, model what's happening using a binomial random variable. So what will be X will measure is the number of bits that have been correctly decoded by the receiver. So either they're correctly decoded or they're incorrectly decoded. So you have a success or a failure, right? And essentially, what this can count is the number of success you get out of n bits that are transmitted. Right? And that will give you some form of probability of error. Yes?
I've just got a question on previous distribution. If the x values were not 1, 2, 3, 4, if they were, say, 0.5, whatever, just a set of discrete values, but we still had equal chance for each of them, would that not be considered a uniform distribution?
You can still use the same principle. The exact value will not be correct of the mean, but you can still compute it. What matters is really that the probability mass function remain the same for all those different values.
So we do still call that a uniform distribution?
You can still call it uniform, but the value of this quantity, for instance, where is it? Right, the expectation here, that value will change, but you can still compute it. Yes, exactly the same way. Okay, so this is an example where actually this is binomial, where you have a communication system, you transmit bits that 0, 1, and what you're looking at is success or failure. Success is actually your bit is correctly decoded. Okay, so this is an example where this can be used. So the question here is, well, what is the probability mass function? So what is the probability mass function? In other words, what's the probability that I have, for instance, X success out of n trial? Right? So how can we compute this? Well, if I have n trial, and I'm looking at X success exactly, I can have success at the first trial. Right? So S1 means I have success at trial 1. And I can have success at trial 2, right? And I can have success all the way to trial X, right? But I'm looking at exactly X success. So that means actually if I have X success here, the remaining trials I need to have failure. Failure at X plus 1 all the way to failure at N, right? That's one event where actually I have exactly X success. Is that the only one? That's not the only one, right? So this is a probability of having this union. I have another event, which is I still have success at the first trial. I may still have success at the second one. But now I have success at X minus 1. I have failure at X. I have success at X plus 1. And then now I have failure at X plus 2 all the way to N. That's another event, right? The first event here and the second one are two different events, right? You can see they're actually disjoint. So those two correspond to two sets that actually disjoint, right? If the first one occurs, then the second one will not occur. There is no intersection between those two, right? It's either this one or this one. But you can have many others, right? So let's look at that. Let's try to now have union over many others. We're going to compute this in a minute. So let's look at the first event, this one here. So this, let's call this A. Right, so probability of A occurring, what is this? I have probability of S1 and S2 all the way to Sx, and then I have failure all the way to Fn, right? How can we compute this probability? We have n trials, they're independent, identical. Yeah?
Since they're independent and identical, just the product of the individual probabilities, so it's going to be the probability of failure is the power of x, and then the success is the power of x, and the failure is the power of the remainder.
That's right, right? So again, they're all independent, so we have done this last week. If you have the probability of two events and you look at the intersection, this is equal to the probability of each event, right? Remember this? So what we have here, this is probability of S1 multiplied by the probability of S2 all the way to multiplied by the probability of Sx, probability of x plus 1 all the way to probability of Fn. So this is P, this is P, so what you get here is P to the x. This is 1 minus P, 1 minus P. What we get here is 1 minus P to n minus x. Okay? Does that make sense? Right? You remember when we had probability of A given B is equal to P of A? That's the definition of independence. Right? So if you have probability of A given B is equal to P intersection B divided by P of B, right? And you take, and you have independence, you have P of A intersection B is equal to P of A multiplied by P of B, right? So this is essentially what we use here. Okay, so this is important, this with independence. Okay, good. So this is P of A. What about P of B? Where B now is, let me take this is B. Right? What will be probability of B occurring? It's the same. Right? It's exactly the same. So you get still P to the x, 1 minus P n minus x. Right? So what you're left with, essentially, you realize that you have a probability of unions, right? And the probability of each of those events, actually those events are independent with each other. I mean, they're disjoint, so there's the union of disjoint events. So by axiom of probability number 3, you can sum those probabilities. So that's going to be P of x equal to x will be P of A plus P of B plus blah, blah, blah. Okay? Each of those, they're all the same. So what do we get is still this quantity, P to the x, 1 minus P n minus x. And now I have a term here. It's essentially the number of events I have in this union. Okay? So this is a combinatorics results, and it's equal to n choose x. This is something you probably have seen in A level. And what is n choose x is n factorial divided by x factorial n minus x factorial. So what do we get is the probability of x having exactly x success is n choose x, P to the x, 1 minus P n minus x. And this is when x is equal to 0 all the way to n. I can have 0 success, I can have all the way to n success out of n trials, right? And otherwise, well, I get essentially 0, right? So that's the probability mass function of a random variable that is binomial. So let me show you an example. So exactly the example I was mentioning before, you toss a coin and you do this 6 times. Right, so n is equal to 6, and your success is head, right? And what you're interested in is having essentially exactly 2 heads out of 6 trials, right? So what do you get? You apply that quantity here. You have 6, choose 2. Probability of P, what is P? Is 1/2. So you're going to have 1/2 square. Right, you're looking at 2 success, and 1/2 here, n minus x is equal to 4. Okay, so this is exactly the probability of having 2 success. If you're looking at the probability of having at least 4 heads, for instance, right? So x is larger or equal to 4. That's P of x is equal to 4. Plus P of x is equal to 5, plus P of x is equal to 6. And you can compute this quantity for each of those values of x, and you sum them up. Okay? So here the main difficulty is to understand essentially what we've been doing here, try to derive this probability mass function, and essentially what we do is actually we rely on the probability principle that we looked at in the past lecture. Good, so what does that look like, this probability mass function, right? So I have an example somewhere in the notes. Yeah, this one here. Right, so what do you see here is the probability mass function for different values. Value of n is equal to 10, but we change the value of p. Right? So what you see is that the probability mass function here, when p is small, essentially you have a higher probability of having a smaller number of success. Right? And as p increases, well, the distribution shifts towards the right, and we have higher probability of having higher number of success. Okay? So what you see from here also is that, well, the expectation here of x, you expect it would be low. Expectation of x here will be around 5. Expectation of x here will be larger. Right? The variance of x here will be small. There is small deviation around its mean. Here the deviation seems to be larger around its means, right? So it's a kind of, the PMF is, if you like, is actually a fatter PMF. And this one here is small, right? So this is something we can calculate. You can calculate those expectations. And this is what we're going to do just in a minute. So before computing the expectation of x and the variance of x, the first thing I want to identify is whether this probability mass function here is indeed valid, right? So is that a valid probability mass function? Right, so you have two conditions for this, right? The first one, you need that all those f of x has to be positive, right? So larger or equal to 0. Obviously, this is the case. The second is that the sum over all x of f of x has to be equal to 1, right? So if we take this and we sum over all values of x here, we should be able to find 1. So how can we see that? Well, I'm summing over all values of x. X goes from 0 to all the way to n, right? And what's my probability mass function is this quantity here. So this is what I'm writing down here. This is n. N choose x, p to the x, 1 minus p, n minus x. Okay, and this should be equal to 1. So how can we know that actually this is equal to 1? Well, we have something that is called the binomial theorem. And the binomial theorem says that if you have two quantity a plus b, and you take power n, well, this is a sum from k all the way to n of nk, a to the k, b, n minus k. So essentially, this is something that you may not know, but you know in a case where n is equal to 2, a plus b squared is what? Is you sum over 3 different values. So you have 2, 0, when k is equal to 0, n is equal to 2, right? Of a to the 0, b to 2, plus 2, 1, a to the 1, b to the 1, and 2, 2, a squared, b 0. This is nothing else than b squared plus 2ab plus a squared. Right? This is the binomial theorem. You know it for n equal to 2, but actually this holds also for n larger than 2. Right? Now, how can we apply this here? Well, you use that, but now a is equal to p, and b is equal to 1 minus p. Right? So what we get here is p plus 1 minus p to the power n here. Right? So this is equal to 1. Okay? So what I'm doing here, I'm saying the sum over all the range of this random variable, this should be equal to 1, right? This is the property of my probability mass function. And so I'm summing for x, the number of actually success I have in n trials go from 0 all the way to n. I sum this probability mass function, and I use the binomial theorem to show that indeed this is equal to 1. Okay, so this is indeed, is that a valid probability mass function? Yes, it's valid, right? Otherwise, little chance we will be looking at this. Good, so once we have done that, let's use this to now calculate the expectation of x. So what is the expectation of this random variable x? Well, this is a sum over x. I'm looking at a weighted sum again over all those x, and I weight by the probability mass function. And now I can write down this expression, right, from here. Let me write. Right, I'm reusing this. This is a sum for x from 0 to n of x multiplied by n, choose x, p to the x, 1 minus p, n minus x. Okay, so first thing we see is that if x is equal to 0, this is 0, so the first term is gone. So what we can write already is sum for x from 1 to n of x, n choose x, p to the x, 1 minus p, n minus x. Right, and now let's write this differently. What is x, n choose x? This is x multiplied by factorial of n divided by factorial of x, n minus x factorial. This is n multiplied by n minus 1 factorial divided by x factorial. This is factorial of x minus 1. Multiply here by n minus 1 minus x minus 1. Here I haven't changed anything. N minus 1 minus x minus 1 here is still the same as n minus x. I haven't changed anything. But by doing that, what we see here, what is this? Only one is following. Please. That's right. Good. So we can plug this into this. And so what we have here is a sum for x equal to 1 to n of n, n minus 1, x minus 1, p to the x, 1 minus p, n minus x. Right, this is. Good, so let's write this a little bit differently. You see I have some x minus 1 here. So it would be good to have some x minus 1 there. So I'm writing this as n and p. I'm bringing p outside. Sum for x equal to 1 to n of n minus 1, x minus 1, p to the x minus 1, 1 minus p, n minus x. And then what we can do is a change of variable. What I can call y is x minus 1. So x is equal to y plus 1. And so if I do that, I get np. And now I don't have x there, I have y. Y goes from what? From 0. When x is equal to 1, y is equal to 0, to n minus 1. So I have n minus 1 here, y, p to the y, 1 minus p here, and I have n minus x. So n minus x is n minus y minus 1. So in other words, this is n minus 1 minus y. Right? So you have n minus 1, you have y here, and you have n minus 1 minus y. So this is very similar to what we had here. What we have here is very similar to what we had there. Instead of having n, I have n minus 1. right? So what is y here? Y actually behaves as a binomial random variable with a certain probability mass function that is given by this, right? This is the PMF of y that is binomial distributed with what parameters? So we had parameters n and p. What are the parameters of y now? I still have p, but now I don't have n, I have n minus 1. Okay? So I'm summing a probability mass function of a binomial random variable over all its range. What's the value of this? 1. Right? So because we just proved just before that actually indeed this is a valid probability mass function, so the sum of that probability mass function over all the values, over the range of that random variable should be equal to 1. So indeed we get NP. So if you get NP and you're looking at this, you have a probability P of 0.5, n is equal to 10, right? What's the expectation is P multiplied by n, you get 5, and you see indeed that your distribution is actually centered around value 5. Okay? Is that clear? So you see actually that trick here, using the fact that the probability mass function is valid, using this to compute something is actually something quite common. And you will play with this in classes with Bernie. You will look at some scenarios like this, and you're going to leverage the fact that a certain probability mass function is valid in the calculation of some quantity, whether it's expectation of x or x squared or variance or some other quantities. Now you can do the same for the variance, but it's simply much more complicated. And actually this is something that you will do in the classes, so you get used to do that. I will not do it here, and the reason for this is because there is a much quicker way of computing this. But the variance is equal to this quantity here. So again, you see that if P is a middle value, 0.5, actually that variance will be larger than if P is small or if P is large. Right, so this is actually something that you will look at in the classes, but a few lectures, maybe in November, what we're going to do, we're going to compute this quantity, but using completely different methods, much quicker. Okay, so this distribution is a bit more complicated to handle. Let's look at another one. So this is that was called binomial. Let's look at another one that is called geometric. So I have now a random variable x that is a geometric random variable with a certain parameter p. And what I'm interested in here is, in contrast to the previous one what we have is we have n trials, we're looking at the number of success in n trials. Here I'm looking at the number of trials needed to get the first success, right? So how many times I have to toss a coin to get the first head coming, right? That's the idea. So how can we compute this? If I want to have my success at trial x, what does that mean? That means that I need to have success at x. What do I need to have at the previous trials? Fail, right? So I have to fail at the first trial, at the second trial, and all the way to trial fx minus 1. Okay, in that case, I get success at the x trial. Right? All those trials, again, are independent, identically distributed. So what I can do is this is the probability of f1 multiplied by probability of f2 all the way to probability of fx minus 1 multiplied by probability of s of x. This is p. This is 1 minus p. And so what you get here is p multiplied by 1 minus p to n minus 1. Nx minus 1. Okay, so this is our probability mass function of having essentially a success at trial x, and I can have success at trial 1, 2, 3, all the way to infinity. Is that clear? Right? Similar idea to what we had before here, but it's simpler to compute because essentially you're looking at, you have only one possible event, right? You need to have x minus 1 failure to get the first success at trial x. So is that a valid PMF? Well, again, this quantity is positive, right? This is always positive. If you don't have this, it's equal to 0. Second thing we have to check is whether the sum of all those, the sum of the probability mass function over the range of x is equal to 1. And so you can compute that the sum for x equal to 1 to infinity, you can have many trials, of p 1 minus p x minus 1. Essentially, this is p multiplied by a sum of x minus 1 to infinity, 1 minus p x minus 1. This is something that is called a geometric series, and this is maybe something that you have seen we've done in other math course, but essentially this quantity is equal to 1 divided by this. So the argument of this comes here, and what you get is this equal to 1, right? So this is called geometric series. This is not something we're going to look at in this module, but this may be something that you have seen in other math modules. Right, so essentially what we get is 1. So indeed, again, this geometric probability mass function is a valid one. Okay, right, so this looks a little bit dry, I know, but it's something you're going to have to get used to it. You have different probability mass functions that are used in different scenarios. I will give you some example when we go to continuous case, where actually this has maybe more application in communication and signal processing. But this is something that actually is used quite extensively. Okay, so one more distribution, and then we're going to have a break. The next one is called Poisson. Right, so this is, I have a random variable x that is Poisson distributed with a certain parameter lambda, and lambda is positive. And so where does this happen? This happens when actually you try to count a certain number of events that occur in space or in time. So for instance, when you're looking at, you're in the supermarket and you try to count, have a way to count the number of customers that arrives at the till, right? You can use a Poisson distribution. When you're looking at a communication system where you have a transmitter again, and you have a receiver here, you have at the transmitter, when you watch a YouTube video, for instance, you have packet of information that arrive, right? So you get packet of information that arrive. The way we model this arrival of those packets is based on Poisson random variable, right? So you're looking at the number of actually arrival per unit of time. It can be per unit of space as well, right? So for instance, when you have a communication systems, you have seen those in London, for instance, you have a city like London, and you take Vodafone, they have to drop those base stations, right? You know those base stations, those very ugly towers you see, that enables you to get coverage for 4G, for instance, right? The way those distribution, the way those base stations actually distributed in London can be modeled also using Poisson random variables, right? But then it's actually is a space domain rather than time domain. So it's the number of actually events, here in this case, the number of the concentration of base station that you can have in in a certain spatial domain. So this is not something we're going to look at, but here, this notion of arrival of packet is something that actually you may see if you take course on traffic theory or queuing theory in the 3rd or 4th year. I don't remember which year it is. You're going to see this, and you can see how actually you can model that. Right, so what does it look like? What is this Poisson PMF looks like? Well, I have probability of x equal to x essentially is equal to e minus lambda, lambda to the x divided by the factorial of x. And I can have this value of x can take many different values from 0 all the way to infinity. So it's essentially the number of events that can happen per unit of time or space. I can have 0 event, I can have 1 event, so I can have 1 packet arriving, 2 packets arriving, or I can have many packets arriving. And it's a function of this parameter lambda, which is the average number of events you can expect per unit of time, essentially. And why we call it average number of events, simply because you will see in a minute the expectation of this PMF essentially is equal to lambda. Right, so is this valid PMF? Right, same question again, fx of x is always positive. Yes, the sum over all x of this probability mass function is the sum for x from 0 all the way to infinity of e minus lambda, lambda to the x divided by the factorial of x. And this is e minus lambda sum from x to 0 to all the way to infinity of lambda to the x divided by factorial of x. Right, what is this? This is Taylor expansion of exponential, right, exponential of lambda. So what you get is e minus lambda multiplied by e lambda. This is equal to 1. Okay, so indeed, probability mass function is valid. The sum over the range of x is equal to 1. Right, so what does that look like? You can have some figures here in the notes as well. Right, so this is an example of this probability mass function, different values of lambda. So when lambda is small, essentially you see that this PMF is centered around small values of x. As lambda increases, this probability mass function shifts to the right, right? And so lambda is the average number of events per unit of time. And you see indeed actually it shifted to larger values as lambda increases. So you see here lambda is equal to 10. The distribution is mainly centered around 10. Lambda is equal to 5. The distribution is mainly centered around 5. Okay, so you will see in the class, you will have some examples of this. You will play with this. What I want to show you is essentially that indeed expectation of x is equal to lambda. So how can we show this? Again, to get a bit familiar with those notions, is a sum over all x, right? So it's a weighted sum. The weights are given by this probability mass function. And now what is this x? I sum from 0 all the way to infinity of x multiplied by e minus lambda, lambda to the x divided by the factorial of x. Right, I can take e minus lambda outside of this sum. And I have x lambda to the x divided by factorial of x, right? And this is e minus lambda. And what do we have? If x is equal to 0, this is 0. If x is equal to 1, I have lambda. If x is equal to 2, I have 2 lambda square factorial of 2. X equal to 3, 3 lambda to the third divided by factorial of 3, and you continue, right? So what you get is e minus lambda. You take lambda outside here, and what you get is 1 coming from here with the lambda goes outside, plus here lambda, 2 divided by factorial of 2 is 1. 3 divided by factorial of 2 is 2 factorial, and 1 lambda comes out, so you have lambda square, and you continue, right? What this is, this is e to lambda, right? Right, so indeed you get that the expectation of x is equal to lambda. Okay, so this lambda is indeed the average number of events that you can have per certain unit of time in your problem that you consider. So how can we compute the variance of x? The variance of x can rely on actually a similar trick. So what is the variance of x? Is expectation of x squared minus the square of the expectation. And what I'm going to do here, I will not compute expectation of x squared directly. I will use a different trick that works well for this specific distribution. I will say this is expectation of x squared minus expectation of x minus expectation of the square of the expectation plus expectation of x. So I'm not changing anything here. I'm just subtracting e of x here and adding e of x there. Right, but then what is this? This is expectation of x multiplied by x minus 1. And what I have here is expectation of x multiplied by expectation of x minus 1. Is that clear? Right, is that step clear? No? Right, so we had expectation of x squared minus expectation of x. Right, and I'm saying that this is the same as expectation of x minus 1. Right, so what essentially you can write here, if I have expectation of x multiplied by x minus 1, this is expectation of x squared minus expectation of x. So far, nothing special. Right, and this is, again, a sum over all x of x squared minus x multiplied by fx of x. So this is the sum over x of x squared fx of x minus the sum over x of x fx of x. This is expectation of x. This is expectation of x squared. Okay? So you see, actually, this is an operation that we're going to do often, is actually the expectation. You can distribute this. Right? When you have a sum of elements, you can distribute that expectation. Okay, so what do we do once we have that? Well, now we can compute expectation of this. So this one we know already. This is lambda. We have done it just before. This is lambda. What is missing is expectation of x multiplied by x minus 1. And so what is this quantity? Again, this is a sum. And I'm doing the same trick as what I did here. So it's a sum for x goes from 0 to infinity of x multiplied by x minus 1 e minus lambda to the x divided by factorial of x. I can take lambda outside, sum x from 0 to infinity, x minus 1, lambda to the x divided by factorial of x. Right, and then we can expand this. And what do we get? If x is equal to 0, this is 0. If x is equal to 1, this is still 0 because of x minus 1. X is equal to 2. I have 2 multiplied by 1, lambda squared divided by a factorial of 2, plus x is 3. That's 3 multiplied by 2, lambda 3 divided by factorial of 3, plus 4 multiplied by 3, y to the 4th divided by factorial of 4th, plus and so on. Right, so what you see here, you have a y lambda square, you have lambda cubed here. I can take lambda square outside. And I have here again, 2 divided by factorial of 2 is 1, so I have 1 here, plus this is 3 multiplied by 2 divided by factorial of 3 is 1, so this is become lambda. This is 3 multiplied by 4 divided by factorial of 4. This is factorial of 2 multiplied by lambda square plus so on. So here, this here, again, is the same as what we had here, is e to lambda. Can you see? Right, so I'm using the same trick as before. Okay, but you have 2 zeros now because you're looking at x and x minus 1. And so what we get is lambda square. Okay, so what we have now here, I have this quantity here is variance of x is expectation of x, x minus 1, minus expectation of x multiplied by expectation of x minus 1. This is lambda square, this is lambda, this is lambda. And so what you get from this is essentially that the variance is equal to lambda as well. Okay, so the expectation is equal to lambda, and the variance is equal to lambda as well. Okay? Right, so it's something you're going to play with Bernie in the classes. You're going to play with those sums. When you have discrete random variable, you're going to have to play with sums. We'll see later on when you have continuous random variable, we're going to play with integrals. Yes, let me take 2 questions and then we can have a break. Yes.
You can come up with this distribution, but they just like solve the equations and come up with it.
So you will see in the classes, you're going to have some other distribution, and you're going to have to compute, for instance, an expectation, and try to find a way to compute an expectation. Yeah.
What exactly does lambda represent?
So here in this context here, when you look at the Poisson distribution, is, for instance, is the average number of customer that is coming per unit of time. So per minute, for instance, you have customers coming at the till, and you have, for instance, 5 customers on average coming to the till per minute, right? But this has a certain distribution. It doesn't mean that you always have 5. You can have less than this, you have more than this, but on average, you're going to have 5.
So you look at the probability that it obeys that average?
No, you're looking at the probability that actually this will tell you a probability that actually you have a certain number of customers coming to the till per unit of time, right? But this has a certain distribution. It may be small, it may be large, right? And what you see there is that if on average you have 10 customers, or let's say I took 5, if on average you have 5 customers per unit of time, per minute coming to the till, well, sometimes you may have 10, sometimes you have a small number, but the probability of this occurring will be dictated by this probability mass function, right? And so why is this used? Is because very often experimentally you can show that actually this is actually what's happening can be modeled using a distribution like this, right? So this actually is a very old distribution. This was invented by Poisson, who is a French mathematician. And many of those distributions, originally they come from some form of experimental validation that they look at something, they have to model it, and they come up with that distribution. And it turns out actually it's used for many different applications later on. Okay, so let's have a break here of 5 minutes till 15 past 3. Okay, let's resume. Right, so let's imagine I have a simple example here. I have x that is a Poisson random variable with a certain parameter lambda equal to 2. And so if you want to look at, for instance, that the probability that x is larger or equal to 2, for instance, so the number event, for instance, some specific event is larger or equal to 2. What is this? This is 1 minus the probability of having x equal to 0 and x equal to 1, right? So you can compute this, right, rather than actually looking at the probability that x is equal to 2 plus probability that x is equal to 3 plus x is equal to 4 and so on. In this case, you can simply say this is 1 minus those two probability, because the sum of p x equal to 0, x equal to 1, and this should be equal to 1. Right, so this is 1 minus probability that x is equal to 0. This would be e minus 2, lambda is equal to 2, lambda to 0, factorial of 0, minus e minus 2, lambda to 1, factorial of 1. And this would be the probability that actually, for instance, you have the number of customers coming to the till would be larger than 2 per unit of time for a given lambda, right? Okay? And so if your lambda changes, that probability would change, obviously. You're looking at p is x larger than 2, so you have 0, x equal to 0, 1, 2. You're looking at essentially that probability, so the sum of those quantities here. And that sum will be different if lambda is equal to 5 or if lambda is equal to 10. Okay? Good. So with this, I think what we have done is to look at the most common distribution for discrete random variables, right? And what we're going to do now is move on to continuous random variables. So what's the difference between those two? Well, in the discrete one, we were looking at my random variable x, what was taking some values here, x1, x2, x3, x4, and so on. What I will look at now is case where this random variable can take, for instance, any values on this real axis between a certain boundary here and a certain boundary there, right? So it can take any values on this continuum on this real axis. Right, so this is continuous random variable, right? Whether it's discrete or continuous, it really depends on your application, right? So I will show you some application where actually continuous is very commonly used. I personally use more continuous than discrete in, for instance, in the field of communication, but you may have applications where actually discrete is more often used than continuous. It really depends on the specific field of application. Okay, so what's the main difference between those two? Well, in here, what we defined was a probability mass function, right? So for each value of x1, x2, x3, x4, actually I was defining a certain probability, right? So I had x1, x2, and I was defining this probability mass function at each of those values of x. Right? So this quantity is really a probability, right? This is really the probability that x is equal to x1, right? In the for continuous random variable, things are not exactly the same. If I have something like this, and I have an interval between a and b, and what I'm looking at is the probability that a certain random variable x is contained between a and b. And now my x is continuous, so I can take any values, right, on this real axis, right? If I'm looking at this quantity, how can I define this? Well, I define this quantity as the area here under a certain curve that I will call fx of x as well, right? Between those two boundaries, A and B, right? Now that quantity here is called probability density function, PDF. So what we had in discrete random variable that we were calling probability mass function is now called probability density function in the continuous domain. But it's not the same thing. Here, fx of x1 gives you the probability that x1 occurs. Fx of x is just a density. That means actually only once you integrate over a certain interval, you actually get the probability. Okay? So the probability of x between A and B is given by essentially the area under this curve, or in other words, the integral of a probability density function between the two boundaries A and B. Okay, so what is the property of this f of x? So this is this probability density function. So what are the properties? The first one, and this is similar to what we had in the probability mass function, is actually this is positive. Right? The second one is also similar, but now I don't have a sum. I'm saying that the integral between minus infinity and plus infinity of this probability density function should be equal to 1. Right? So what that means is, again, the same as this axiom 2 of probability. The probability of the universal even is equal to 1. Here, what it means is that if I integrate over the entire range of this random variable between minus infinity and plus infinity, I should get 1. Okay? Now, here, the sum of those f of x was equal to 1. That means actually each of those f of x were actually smaller than 1. Right? Here, with the PMF, we had that sum of is equal to 1. And each of them here are positive. Right? That means that each of those fx of xi are actually smaller or equal to 1. Right? The probability here of x is equal to xi is always smaller or equal to 1. Right? Here, I can have case where fx of x can be larger than 1, because this is just a density. It's not a probability, it's a density. Right? So where this can happen, so an example where this can happen is, for instance, you have a probability mass density function that is equal to 0, and between 0 and epsilon is non-zero, and you get something like this, equal to 1 over epsilon. Right? So what is the area under this curve is essentially this. 1 over epsilon multiplied by epsilon is equal to 1. Right? But if epsilon is smaller than 1, this probability density function will be larger than 1. Okay? So it's a density. Right? So it's only once you integrate over an interval that you get a probability. Right? But that probability still has to be small or equal to 1. Right? If you integrate this over the entire domain, or the entire range of that random variable, from minus infinity all the way to plus infinity, you should get that the probability is equal to 1. Good. So, in general, if you have the probability that a certain random variable belongs to a certain domain A is essentially the integral of this probability density function over that domain A, right? So if I have a PDF here, and I have a certain domain here, a certain interval A, that probability of this occurring essentially is this area. The area under this curve here in this interval A is essentially the integral of this probability density function in that domain A. Okay? Good. So this is about probability density function, right? What we have looked at with the probability mass function, with the discrete random variable, we looked at the case of the CDF, cumulative distribution function. Right? So here is the same idea. If I'm looking at a continuous random variable, evaluate at a certain point A, what is this? Is the probability that x is smaller or equal to A. So if now I have a probability density function here, and I have a certain value A, what I'm looking at here is essentially this whole area here. I'm looking at the probability of x being smaller than A. Okay, so I integrate essentially between minus infinity and A this probability density function fx of x. If I take a value of B here, and I'm looking at the CDF evaluated at B. This is probability of x being small or equal to B. If B is larger than A, this is equal to that. Right? The integral between minus infinity and B of fx of x dx. So if you have A is smaller or equal to B, then you're going to have that actually the CDF of B, A will be smaller or equal to the CDF of B. Okay? So if you draw the CDF of this, what do you get? Typically, you're going to get something that goes from 0 to 1. Right? So this is the CDF. And if you're looking at A, this is the value of the CDF of A. If you look at B, this is the value here of the CDF at B. So this would be fx of B. This would be fx of A. Okay, so the CDF is actually a non-decreasing function, right? If you take two values A and B, B is larger than A, the CDF at B will be larger or equal to the CDF at A. Good, so how do we link CDF and PDF? Well, you can see that actually the CDF here is essentially integral of a PDF. So the PDF will be a derivative of the CDF with respect to x. And this holds whenever this derivative exists. And in all the problems that we're going to look at, typically this derivative exists. So we can use that definition, right? So what if I want to compute some probability now? So I have this distribution, I have A and I have B, and I want to look at this quantity here, right? So I have essentially here two options. I can say this is the integral between A and B of the probability density function of x, right? Or I can say this is the CDF of x evaluated at B minus the CDF of x evaluated at A. So that's two different ways of calculating. You either take the CDF of B evaluated at B, which is all this area here under the curve, minus the CDF of x evaluated at A is all this area under the curve, and what you're left is this area here. Or you can use the definition directly of integrating the probability density function over a certain domain between A and B, right? So those are two equivalent ways of actually computing that probability. Right? Is that okay? I think this should be this should be fine. Good, so let's look at some example. Right, I have an example here where we're looking at a certain probability density function that is given by cx squared for x contained between 0 and 2, and otherwise it's 0, right? And what we're asking here is find c such that fx of x is a valid probability density function. Right, so first one, fx of x has to be positive, so that means actually c has to be positive. Second one is the integral between minus infinity and plus infinity of this probability density function should be equal to 1. Right, so if you integrate this quantity, right, I plug this here, what you get is the integral between 0 and 2 of c x squared dx, right, that's c x cubed over 3 between 0 and 2, that's c 8 over 3, right? So you choose c such that c 8 over 3 is equal to 1, so c is equal to 3 divided by 8. Okay? So with this, you know that if you choose c accordingly, 3 over 8, then this PDF is indeed valid. Good, so if you want to compute the CDF of this, now you have a valid PDF, right? What is the CDF? CDF of x. Well, you're looking at the probability of x being smaller or equal to a certain quantity, right? So if u is smaller than 0, you know that from here the PDF is equal to 0, so the CDF will be equal to 0, right? If u is between 0 and 2, what you get here is the integral between minus infinity and u of fx of x dx. If u is larger than 2, what should we get? It should be 1, right? Because the integral of this over its domain, right, should be equal to 1, right? So what do we have here? Integral of minus infinity to u of fx of x dx is here the integral, because of this, between 0 and u of 3 over 8 x squared dx. And so what you get here is 3 over 8 x cubed over 3, 0 u, right? And you get u cubed divided by 8, right? So this is your CDF, right? And so what it looks like is you have 0, you have 2, here the CDF is equal to 0, and then it increases like this, u to the third, all the way to 2, and then at 2 is essentially equal to 1. Okay? So if you calculate the probability at u is equal to 1.5, essentially this is going to be your CDF at 1.5. Okay, I think that should be fine. Okay, so we looked PDF, we looked at CDF, we looked at expectation and variance for discrete random variables. So what is happening now for continuous random variable? Well, I can still define an expectation, right? Or theoretical mean. I still have expectation of x, which is my mu. But now, since I have a continuous random variable, I do not sum over the range, but now I take an integral, right? So this will be the integral between minus infinity and plus infinity of x multiplied by its weight, essentially, right? So this is like a weighted average, where the weight is again given now by fx of x, by this probability density function. Right, so if you have expectation of ax plus b, right? What do we get is the integral between minus infinity and plus infinity of ax plus b multiplied by the probability density function. So that's ax multiplied by the probability density function plus b multiplied by the probability density function. I integrate over x. What is this quantity? 1, and this is expectation of x, right? So you get exactly the same as what we had earlier on with discrete random variable. If you take a random variable x, you multiply by a and you shift it by b, right? Indeed, that theoretical mean is such that the theoretical mean of x is multiplied by a and shifted by b, right? So if you have a distribution that is something like this, where this is my mu, expectation of x, right? And now I'm choosing here x plus b. That distribution will be shifted, for instance, to the right, and now I'm going to have mu plus b. Okay? Is that all clear? Good. So let's look at the example we had just a minute ago. So we had this probability density function is 3 over 8x squared for x between 0 and 2, and otherwise it's 0. So what is this expectation of x? Well, again, is the integral between minus infinity and plus infinity of x multiplies by the density of x. This is the same as the integral between 0 and 2 of 3 over 8 x cubed dx. So x multiplied by x squared, now you have x to the third. And so this is 3 over 8, x4 divided by 4, 0 and 2, 3 over 8, 16 over 4, right? And this gives 3 over 2. Okay? Right, so this is essentially just calculating one integral. Right, so it's clear. So essentially you're looking at here again, expectation, the same idea as what we had in the discrete random variable. You're looking at this mean, where this distribution is centered around, mainly. Right, the variance, on the other hand, will be the spread of the distribution around its mean. Right, so how do we define the variance? Now that we have a continuous random variable, well, it's actually the same idea. The variance of x is still expectation of x minus mu. So the expectation of the square of the deviation between x and its mean. So if I have a random variable around mu here, that's its mean, and I have something that looks like this, or if I have something that looks like this, right? Which one has a larger variance? The red one, right? The distribution, the spread of the distribution around the mean is actually larger when in the red case. So the variance of the red distribution will be larger. So sigma, which is the square root of this is still the standard deviation. So same quantity, same notation as standard deviation, same terminology as what we had with discrete random variable. And we had this relationship that we can write this differently, right? So let's look at this. If I have expectation of x minus mu square, how can I write this differently? I can say this is the integral between minus infinity and plus infinity. I'm using the definition of expectation of x minus mu square multiplied by the probability density function of x. And now I can distribute that term. So it's integral between minus infinity and plus infinity, x squared minus 2 mu x plus mu squared multiplied by the probability density function of x. This is the integral between minus infinity and plus infinity of x squared pdf of x minus 2 mu integral of x fx of x dx plus integral mu square integral minus infinity plus infinity of PDF of x. Okay? I'm just distributing that integral over those three terms. What is this one here again? This is 1. What is this? This is mu. And this is expectation of x squared. So we have expectation of x squared minus 2 mu square, mu multiplied by mu, plus a mu here, square. So expectation of x squared minus mu square is expectation of x squared minus the square of the expectation. Okay? Exactly the same relationship as what we had with discrete random variables, right? Same holds. But this is shown differently using now the definition of expectation for continuous that is based on an integral and a probability density function. Right, so same as discrete, this is always positive, right? This PDF is positive, this term is positive, this integral has to be positive, so this is positive. So expectation of x squared is always larger or equal to the square of the expectation of x. That holds for discrete random variable, it holds for continuous random variables. What if we have variance of ax plus b? So again, what I can do here, I can say this is expectation of ax plus b minus a mu plus b. Right, so this is expectation of ax plus b minus a mu minus b square. The b cancels, and I get a square expectation of x minus mu square. This is a square variance of x. Okay, so here I can do it again. And you can show it differently. You can take the expectation and then do exactly what we did. You can say expectation is actually now the integral of this quantity multiplied by the PDF, and you can do this equivalently. Here I'm using the short version where actually I'm distributing, not distributing, but essentially you see actually those terms cancel each other, and so you get essentially exactly the same as what we had before. This is nothing else than the integral between minus infinity and plus infinity, x minus mu square multiplied by the PDF of x, right? What we had earlier on was the same, but now that was a PDF probability mass function, and we had a sum here, right? But the idea is the same. The relationship still holds. So what you see here, again, if you multiply x by a, the variance is now multiplied by a square. But if you shift by b, well, the variance does not change, right? So y does not change. When I take this distribution here and I shift it by b, well, nothing changed on the spread of that distribution around its mean. The mean has been shifted by b, but the spread around its mean has not changed, right? The mean was here. Now we had mu was here, right? I shifted by b, right? But that spread here has not changed. The measure of the deviation around its mean has not changed because I shift just by b this quantity, this random variable x. Okay, so before we stop, let me just go back to this example again. Right, just to show you how we do this. So we have a probability density function that is now 3 over 8 x squared. X is between 0 and 2, and otherwise it is 0. And so if you want to compute the variance of x, you do expectation of x squared minus the square of the expectation. Right, this is one way of doing it. And so expectation of x, we have done this. This is 3 over 2. Right, so what is left to compute is expectation of x squared, and so what you do is integral between 0 and 2, x squared multiplied by 3 over 8, x squared dx, right? and you can compute this, what you get is 12 over 5, and so you get 12 over 5 here, and you get 3 over 20 there. Okay? So just direct computation of an integral, no major issue. Okay? So you see variance and expectation, actually the same idea, whether it's discrete or continuous, right? You can use the same tools. They fundamentally rely on different principles because one is based on a probability density function, the other one on the probability mass function, right? But the properties actually carry on between discrete and continuous. The definition of variance and expectation, essentially, there is a similarity between the two. Right, so let me stop here, and what we're going to do next week is we're going to jump into different distribution for continuous random variables.